Hello, everyone. Welcome to TI's new product update webinar series. My name is Jyah, and today me and Gavin will be speaking about making electricity meters smarter. During the presentation, we will be having a live Q&A, so please put your questions down below in the box and we'll answer them throughout the presentation. Today, we will be discussing a little bit about some of the system level requirements that are common inside of metering architectures, as well as discussing TI's new ADC product and what those requirements are, and also what our products address. We will also discuss a little bit about the reference design for the AMC131M003 and ADS131M0x in one-phase and three-phase applications. We will also be discussing how does energy metering scale across different end equipments, as well as provide an overview of the metrology required for this type of metering, and then we'll conclude with a summary. So to start, let's discuss different electricity metering architectures. So when you're trying to do energy metering, you have three main different options that you can be using. One is called SoC, which is system on chip, which has all of the metering calculations inside of this one chip. So it does all of the calculations as well as metrology all in one package. We then have ASSP, which has fixed parameters. It doesn't have options for advanced metrology, but it does provide a little bit of flexibility with additional components. But with this solution, you will need to also have the processor metrology to go along with this solution. And then finally, we have the discrete solution, which is what we will be discussing more in depth, which goes with the ADS131M0x and AMC131M0x families, which provide you an unlimited amount of parameters. It allows you to have advanced calculations, hence making electricity meters smarter. It also is very high in accuracy and also provides a lot of flexibility when it comes to your solution that would work better for your system. However, it does require more work when it comes to metrology, which is just the calculations that you would be doing with the data from the metering. And so what we have provided is a metrology library to help make this easier for you to do, which you can access with the link to the energy library for starting of development of your metrology library. This solution is also lower cost. So for metering, there are three different types of sensors that are commonly used. The first is the current transformer, or also just called CT. This one is phase calibration. There's also Rogowski Coil, which is very similar to the current transformer, however, would require isolation to be, also has inherent isolation. Rogowski is a little less common through customers, so traditionally what you will see would be the current transformer metrology. And then finally, the shunt sensor, which is not inherently isolated, but is anti-magnetic through just the nature of the sensor. So some of the solutions that we provide are the ADS131M0x for single phase CT, Rogowski, or shunt meters. And then for polyphase, you would also be able to use the ADS131 family for both CT and Rogowski because of the fact that it has natural isolation. However, TI had to develop a new solution so that customers could do shunt metering, which is where the AMC131 comes into play. We will discuss a little bit more about this part later on in the session. However, what we will know is that this will help with providing that isolation that is required to do shunt metering. Now, one of the reasons why people do prefer or are moving towards shunt metering is because of the fact that it is anti-magnetic tempering and also provides a smaller form factor, which is one of the bigger benefits of this type of sensor. Below what we provided is for shunt metering. As you can see, the table at the bottom, this is discussing some of the safety and standard requirements for shunt metering. So one thing that we do want to discuss is give you a little bit of a view of how do TI's new ADC help with enabling energy metering. Well, the first thing, as you can see, for both C, which is current transformer, and shunt metering, you can do from one phase all the way up to 3 phases with or without a neutral measurement. You also get RMS measurements of AC signals, and it can also do an ADC bipolar input range. You'll also have the phase-to-phase synchronization. However, that is only in the CD implementation. The next thing is you will have functional safety standards. So you're going to get galvanic isolation for both the digital and power measurements. And finally, you're going to get some of the best-in-class AMC performance with the shunt implementation, which would go into that AMC131M0 family. And then finally, for both CT and shunt, you're going to get excellent ADC bandwidth. So here you can see more of a in-depth view of the circuits for both the CT and a 3-phase shunt. So on the right here, we'll see that we have this 1-phase shunt measurement. As you can see, both the current transformer and the shunt are using the same architecture here. We're using that ADS131M0. That is because with CT, you don't need that additional isolation, but also with the shunt measurement, because we only are doing 1 phase, we do not require that additional isolation. However, when we go to the 3-phase shunt architecture, you will see that we do need that additional phase-to-phase isolation, which you can see in the different chips here. However, we do also need that power isolation as well. So this is what we have kind of in this line that is being provided by the AMC131M0x architecture, which will reduce the amount of additional components needed for the customer when traditionally doing this type of architecture with the ADS131M0x. So because of the AMC131 M0x, you will now be able to remove over 36 additional components that you would traditionally see without having this part, because of the fact that it's providing that data and power isolation. So as we can see here, here's just a little bit of the description of the part to really highlight the benefits that you will be getting from using this device. So the biggest benefit here would be that data and power isolation, helping reduce costs traditionally seen in this architecture by taking care of a lot of that internally. So a lot of those isolation needs are integrated into this device. You'll also be able to do synchronization between the different devices, making it easy to do that phase-to-phase measurement, as well as having built-in temperature measurement for easy temperature compensation as well. As you can see, this is a high accuracy device that is also low in power and can be used in a variety of different end equipments and industries. So here is our new solution simply being shown. This example particularly is a 3-phase current and voltage architecture with a shunt neutral measurement that is using the ADS131M0. One of the best benefits of this part, as we said, it has that isolated data, it has that isolated power, it has that same feel and performance of the ADS131M0x, the non-isolated version. However, it is a small size meter front end for the industry that requires no need for stitching capacitors or those additional isolation components. And finally, remember that energy metering is not just about electricity meters. This can be used in a variety of different end equipment. This breakdown shows the different end equipments that it can be used in. with the different type of sensors. So as you can see, CT and shunt are most common, but not only is this used in electricity metering, it can also be used in AC charging, DC charging, as well as PDU systems, and also energy storage units.
All right. Thank you, Jyah. Now we can go ahead and start looking at some of the upcoming reference designs we have featuring this AMC-131M003. So my name is Gavin Loetta. I'm the second presenter here. I'm on the systems team, so we can go over some of the systems that we have coming up here. Our first one here is a single-phase shunt emitter reference design using the AMC-131M003. This was sort of an in-between process while we were working with the AMC-131M003. We have this one here to just kind of show off the initial features, showing that we have a class 0.2% accuracy, measuring up to 100 amps with a 200 microamp shunt. We are able to show high performance with up to 32 kilosamples per second sampling rate. The integrated digital isolation and power, of course, that's inherent to the AMC-131. And then on this actual reference design, you'll notice that it's very similar to the solutions that Jyah was showing. What we were showing here is that you can actually use one of the newest microcontrollers that we have here at TI coming out, the MSP-M0G, and we have an entire MCU-agnostic energy library that basically shows you how to do active and reactive energy and power, the RMS current and voltage there, power factor, line frequency calculations. All of this is within our energy library that comes with already on our reference designs here when you get them from us. And it allows you to evaluate the AMC-131 or really any of the precision ADC parts, actually be able to put power through it and see that the calculations that are coming out are working and that they're the accuracies that you're looking for there. Some of the benefits is that the same family ADC can be used for both the single phase shunt as well as a polyphase CT. So basically what I'm trying to get at here is this energy library that comes with our reference designs we'll be able to work on the CT applications as well as the shunt applications here. And we also, as I said, it's MCU agnostic. So while our reference design is featuring the MSP-M0G, we actually have multiple microcontrollers here that we've been able to get the energy library working on. So if you wanted a higher end microcontroller with maybe some more safety features, we'll be able to cover that. This is looking a little bit more in depth into that polyphase isolated shunt solution that Jyah was showing just a few slides earlier here. As you can see, we're still boasting the same 0.2% accuracy on the three-phase metrology up to 100 amps. Going up to 32 kilosamples per second sampling rate. And we also have an additional ADS131M002, as you can see at the bottom, to do the neutral tamper detection here. We have the integrated digital isolation and power again, that's part of the AMC. And the MSP-M0G that's on here is a Cortex M0, ARM Cortex M0 microcontroller. And it supports that energy library I was talking about from before. This is something that we are in the progress of working on. We have the boards and we're starting to do some testing on it. So you can see that this reference design will be coming out very soon to be evaluated by you all. But I also wanted to touch a little bit more on the energy library itself. This is one of the main things that you will be getting with the reference design, that will be available with the reference design. So go over some of the features that we currently have, and then some of the features that we're going to be working in this next month. You might be seeing it pretty soon here. So some of the basic metrology calculations, that's the active and reactive energy, the apparent energy, the active and reactive power. and the RMS voltage and current. These are features that we have on our boards right now and we're able to test in the lab. We've been testing them on our, as Jyah was saying, we have a CT three-phase metering reference design, and we've been able to test these very successfully on there, actually getting accuracies a little bit closer to 0.1%, which we're very happy about. But we're looking on to trying to add some of these other features here, the per phase total harmonic distortion for voltage and for current, supply voltage dips and sags, swells, interruptions under and over deviation, voltage phase-to-phase angle, and per phase zero crossing. So these are features that we're currently working on implementing into the energy library and will be kind of showing up here pretty soon. So one question you might be having is why would you go with the shunt over the CT solution? As I said, we have the CT-based solution and a shunt-based solution. As Jyah was saying, the CTs are prone to being oversaturated. So in areas you might have some tampering where somebody's putting a magnet on your meter, that might saturate your CT, causing the issues with metering and with having being able to accurately measure how much energy that they're using. That's where the shunt solution comes in handy here. You can't put a magnet up to it, but there is still ways to tamper with this. That includes neutral tampering, but that is why we thought ahead and made sure to add a neutral tamper detection line onto this reference design, so that whenever you have kind of a better view of what this entire system might look like when you get the reference design. So as I said, this energy library is MCU agnostic. We've been able to get it working on a couple different MCUs here. Our cost-effective three-phase emitters, we choose to go with the MSP-M0G. We've been able to successfully get up to 8 kilosamples per second plus at 30 bytes read-in and with a SPI clock of 19.95 megahertz. We've been able to get that working on with the CT design, and we recently were actually able to start seeing it with the AMC design as well. For very cost effective, so even if the MSP-M0G is still a little bit too pricey, we have the MSP-M0L. For that one, we've been able to successfully read 2 kilosamples per second with a SPI clock of 16 megahertz there. And we estimate that it should be able to get up to 4 kilosamples per second with that 16 megahertz. We've been focusing, though, on the MSP-M0G. That's per second is estimated right now. Now on the smart metering side here, so this is if you need BLE-enabled 2.4 gigahertz or the sub 1 gigahertz or even both, or hardware security and encryption. That's where you would actually look at our family here. These are some of our wireless MCUs, and they've been tested in many different end equipment designs. So we've been able to successfully get our energy library ported to these wireless MCUs as well, so that you can evaluate these and start, in case you need more of the high end there with the hardware security encryption or the wireless capabilities. We've been able to get it up to 8 kilosamples per second with a 6 megahertz SPI clock. So in summary here, we offer a dual chip solution with a high precision ADC plus a TI microcontroller there. We have solution options for multiple different cost points, as I showed in the previous slide, with some of our lower end with the MSP-M0G up to our higher end with the wireless microcontrollers that we have available. We provide an example application library when you receive a reference design, and be currently available on multiple TI wired and wireless microcontrollers, the MSP-M0, or if you need a Cortex M3, M4, or up to M33, that would be on the wireless microcontroller side. And we also have energy metering architecture can be used for a variety of systems, as Jyah was saying, not just for metering, but going into AC and DC charging as well. So at this point, we can take a look at some of the questions here. So
I see one question. Oh, sorry, I'll interrupt.
No, by all means.
I see one question asking whether the AMC131M03 would work for split phase metering as well. The answer to this is yes. Anytime there is that phase-to-phase isolation needed, the AMC131M03 would also work for that type of architecture. There's also one discussing what would the benefits of using the M0 be for metering. Gavin, could you address that question as well?
Yeah, so some of the benefits of the M0 here, has a cheaper price point for one. And that's really, we really wanted to try to kind of reach that very low cost features there. And that's the main reason. It does still have some hardware encryption on there, but it kind of is just enough to handle a lot of the basic metrology and a lot of the features that we were talking about on the energy library. Has just enough the processing power and the SRAM there to be able to run our energy metrology library. That's really the main benefit of the M0 family. I want to give some more time here for some more questions. All right. Well, thank you everyone for joining today's session. Please be sure to register for next week's session by visiting ti.com/NPU. Thank you and see you next week.